Good morning, everyone. My name is Lukasz Lopacinski. I'm representing IHP and project 6G-SENSES, and today I would like to tell a few words about OTFS. So firstly, I will give you a short introduction to the topic. Then we will discuss OTFS frame pilot-based channel estimation, frame processing, some SDR experimental result for communication, and then some SDR also sensing results. 6G-SENSES project consists of 11 partners from 7 countries. We work on 6G RAN technologies, for example, cell-free MIMO, OTFS, and the main aspect is oriented here on sensing. Now, please imagine that we have such a following situation where we have one base station somewhere on the highway and also a car where we would like to provide wireless internet. Everything is easy and simple until we have line of sight communication with one path. Yes, then here actually every communication standard will work. So OFDM will work, single carrier will work, and everything else. The situation is a bit more complicated if we additionally get some additional reflections from different cars. So firstly, this line of sight will be affected by Doppler shift, yes, because of the movement of this car. Then this path will be additionally affected by move of this truck. This car is also affecting the other paths, yes, this path, and also this car also have another velocity and also in another direction, yes. So every of this path will show different Doppler shift, and in total we will get a Doppler spread. And this actually channel is perfect for OTFS, and OTFS is perfectly suited to solve this situation. Now let's take a look on the OTFS frame. In OTFS, we actually transmit not vectors, but matrices. So we need to assemble our data into a matrix. Why matrix? Because we need to represent the signal in the delay and Doppler domain, and we need to do this two-dimensional representation. Here we see the pilot, which is used for channel estimation, and we have also some zeros surroundings. And I will explain the need of using these zeros later in next slides. And here is our data. This data in this delay Doppler domain, it is just simply, for example, QPSK or QAM modulated signal. Here we have QPSK, so that the ABS or the amplitude of those symbols is always equal to 1 or around 1. Yes, it depends how we will encode it. But this is nothing else like data actually modulated for single carrier or for OFDM, so that are just complex numbers which represent constellation point. Now I would like to explain you the importance of this pilot and these zeros in the delay Doppler domain. So now if we consider just simple AWGN channel transmission, so this is our transmitted frame. So we remove completely the data out of the frame and we will observe only the pilot and we will see what is happening. So if we transmit over AWGN channel, here is actually nothing interesting because we just get some random noise to every of this bin in the delay Doppler and also to the pilot. So actually this channel is very simple and doesn't change anything in our pilot geometry. But if we consider more practical channel, for example, we will have one transmission path with some Doppler shift, yes, then the situation will be slightly different. So what we will see that this pilot will be shifted among the Doppler axis, yes. So originally it was here on the 0 position according to the Doppler axis, and now it is shifted. And from this shift, we know exactly how much was the Doppler shift. So we can estimate the difference in the velocity between the transmitter and receiver. Yes, of course, we have still some noise, yes, random noise for the other symbols, but actually here we very nicely can see that, that there is velocity difference between the transmitter and the receiver, and we have most probably line of sight communication because there is one path, one pilot. If we have multipath propagation, and let's say that are 3 static paths, then this pilot will be copied 3 times. Yes? So each path will create a ghost image of this pilot. So this can be, for example, line of sight line. This is one reflection, and this is the second reflection. So here we also see the distance between them in the delay axis. So we know the time difference between these 2 paths and between this second and third one. And we can also estimate it quite precisely. Here we see that all of these pilots, these copied pilots, they lie on the Doppler axis 0. So it means that was most probably a fully stationary conditions. Yes, so we have probably the transmitter and receiver are not moving, and also the other reflections, they are coming from static objects. If we consider a similar path propagation, multipath propagation, where one of the paths is additionally affected by Doppler shift, then this situation can look something like this. So we have here most probably line of sight, reflection from a static object, and reflection from a moving object. Yes, and this actually the affected Doppler, we can see here, we can read it from the Doppler axis. So what's important here to show, actually this channel estimation, pilot-based channel estimation OTFS is nothing else like a radar image of our environment. So we see the channel geometry, let's say. We directly have the sensing, yes, embedded into channel estimation. And now on top of this sensing, we put communication, yes? So this is actually adding to the sensing the communication part. So we take the radar and we try in the radar enable communication. So that's actually how OTFS works. Now let's take a look on OTFS frame processing and how to go from the delay Doppler domain to the time domain. So as I said before, we need a two-dimensional signal representation, for example, a matrix. One of these symbols can be a pilot, for example, C1, and the others, they are, let's say, another complex numbers which represent our symbols. Yeah, for example, 1 minus I or 1 plus I or something, anything else, or 0.71 plus 0.71 I, anything, but just some complex numbers which represent QPSK constellation. What we do? Okay, the first problem what we need to solve here, we need to go from the delay Doppler domain to the time domain, because our signals we always send in the time domain. So what we do? We use something called like an inverse ZAC transform, yes, if we consider ZAC transform based OTFS transmitter, and we then in the first step we convert this delay Doppler domain to delay time domain, yes, so we need to change this dimension. If we want to change this dimension, it means that we need to do something on these rows. And what we do, we use this inverse ZAC transform, which is nothing else like computing IFFT on the rows. And then we change this Doppler domain to the time domain. So inverse ZAC transform sounds very complicated mathematically, but it is nothing else like performing IFFT on the row. So very complicated name, but very simple practical operation. Then what we do later, now we have still the problem that we have this delay representation, which we don't want to have it. We want to just only have the time. We want to represent the signal in the time domain directly without any additional delays, nothing like this. So what we do serialization. So we reshape this matrix to the vector form, and we simply, how we do it, we take every of this column of this matrix and we reshape it to a vector. And then we have time, we are in the time domain, and those complex numbers are just simply IQ samples. Here it's also important to say that we need on top of that pulse shaping. So we need to perform pulse shaping on the signal, and then we have the simplest OTFS transmitter in the simplest form, which will have a kind of performance, yes, but actually this will be, yes, the simplest OFDM transmission chain. The receiver, actually we do everything the same, but in opposite direction. So firstly, we get from our ADC samples in the time domain, and that will be IQ samples represented like complex numbers, like in OFDM or every other single carrier transmission chain, anything. Yes, this will be the same like in other systems. So what we do as first? We need to do firstly our matrix. So we need to represent the signal two-dimensional. So we do reshape, but this time we go from vector to matrix, and we do it column by column. And now we will be then in the time delay domain. So what we do, we need now ZAC transform. Yes, so this ZAC transform based receiver, we can say. And actually the ZAC transform changes our delay time representation to delay Doppler. And what is this? It is nothing else like FFT performed on the rows. Previously, we were using here IFFT. So now we have opposite operation. So we do FFT. Here we have inverse ZAC transform, and now we do direct ZAC transform. So this is actually how the simplest OTFS receiver can be designed. Yes, so very simple operation, not more complicated than OFDM, because we simply do FFTs on the rows. So this is really like OFDM is doing. We have also another possibility how this OTFS transmitter or receiver can be done. We can use it also OTFS like a precoder for OFDM. So we will have two domains. So we will be working in delay Doppler domain, in this matrix, but also we'll have frequency domain. So let's say OFDM domain. So how it works. In such a case, we need to use inverse symplectic finite Fourier transform, yes, so which actually convert us from delay Doppler domain to this frequency time domain. And now, how it is made. This is again a very complicated name, but very simple practical operation where we have IFFTs on the rows and FFTs on the columns. So this is actually what this inverse symplectic finite Fourier transform is doing. And then we are in this time frequency domain. So it means each column of this matrix is actually an OFDM vector. So we are now in this frequency domain where we can do filtering, for example, rate changing or anything we want. Also, we can do here sensing in this domain very easily. But still, we need to remove this time representation. Actually, yeah, we need to go to the time domain. So what we do just normal OFDM. OFDM on this OFDM vectors, we just do IFFT. We are in the time delay. This we fix by serialization, and we are in the time domain, and we just send it this IQ samples like a complex number. Pulse shaping can be done here in the OFDM. Therefore, pulse shaping may not have to be necessary here. So this is a bit advantage of this processing. Please take a look here that here we have FFT. Here IFFT. So it means that these two operations are canceling each out. Yes, so actually they are they are not needed, but they are only needed because we want to be in this frequency domain here. Therefore, it's performed. So it's very redundant operation. Yes, but this is what we pay to have this frequency domain representation. But actually, as you can see, processing is simple. Excuse me. Now I would like to show you some experimental results made with SDR. So firstly, if we just take two USRPs and we simply connect them together by a cable, so we actually don't have any wireless channel, just copper medium, just 50 ohm matched cable. Then if you transmit between the transmitter and the receiver a simple OTFS frame, you may expect such a view. So those are our data symbols. Here is our pilot. And as you can see, this constellation is very noisy. Although the power of the signal was very well adjusted, we get some such initial noise. So we see that this SNR is strongly degraded. Okay, strongly because on the cable, I would expect this EVM really zero or almost zero, but this noise here is quite significant, like for a cable communication. This is caused actually due to these little side lobes around the pilot, and actually the same side lobes are built for those data symbols, and those side lobes are doing this noise. And from where it came from? OTFS is very sensitive to STO, so sampling time offset. If this sampling time offset is not fixed digitally after sampling from the ADC, we get this initial SNR degradation. And actually in OFDM, you will not see this problem so clearly, but OTFS is very, very sensitive to STO. So this is the first thing what you need to do. And actually, never mind how it will be done, at which stage, but before you go to the delay Doppler domain, you have to fix this STO. In other case, you have some initial degradation of SNR, which you probably will not see in OFDM because channel estimation there may fix this slightly. Yes? So it's not so sensitive as OTFS is. If you now remove this cable and will do line of sight communication in the office, then this constellation may look like this. So now we have significantly more noise, but it's expected. But here is happening some interesting. So we see this pilot is doubled. And actually, this is mainly line of sight communication. So we should see here one pilot, very strong one pilot, and maybe some small other multipath components, but this is too strong in my opinion. So how to interpret this picture? Actually, why it's happening? Because we have non-integer delays. So the pilot has been received and the symbols are received between the samples. And we have non-integer delays, and basing on the signal propagation time, so how it's the distance transmitter and receiver, this payload was received between two ADC samples. So this not necessarily means that we have two paths. We may have one path, but there are non-integer delays. There are also, we see some side lobes here, which are not corrected by STO algorithms, but actually, yes, so this we see that mainly we have this non-integer delays in practical application, which are not necessarily considered in theoretical work. So in papers, you will always see very perfect, nice constellations for delayed Doppler when the pilot is always a single peak, and where these peaks are very clearly divided and so on. So this in practical application doesn't have to happen. Yes, it also depends on the sampling frequency and in bandwidth what you have and how is the grid of your delayed Doppler matrix. But such beautiful images, like you can see very often in simulation, you will never get in reality. Non-line of sight, for example, here we did we cut the line of sight by some metal plates, pretty huge metal plates, so we are sure that there is no line of sight component. And here we probably see two paths which are split to three ADC samples. Yes, this will be my interpretation of this environment. Quite a lot of noise, and this noise have to be also fixed by MRC decoding and bit detection algorithms like MRC or message passing algorithms. Now let's take a look on some sensing experiments that we did. So for the sensing purposes, we built such a practical demonstrator where we have transmitter antenna. This is a sensing antenna for the transmitter. Yeah, so actually here we send the data, and this is only sniffing the reflected frames to find the position of the nodes, of the communication nodes. Then we have one still reflector, which is just a passive element. It is just only reflecting, so we use it for getting some nice reflections, so that we are sure that this is the wanted reflections what we are sensing actually. And then we have one communication node with receiver antenna and also with metal plate, where we can also find its position in the room. So we use 5.3 gigahertz carrier frequency with 160 megahertz bandwidth. We use X310 USRP, so therefore we are limited with this bandwidth, and this carrier frequency is also the highest frequency which we can use for this power amplifier, so it still has pretty high power. If we go above 5.3 gigahertz, then we see strong reductions in the PA power. Therefore, this is the maximum what we can do here. And also there is interference with wireless LAN, so that with this frequency here in IHP, we have to be very careful, but 5.3, it's a kind of compromise which we can use due to the interferences and also the power amplifier efficiency. So we build such a scenario. So we have transmitter antenna, we send the data. This is reflected from this static metal plate. Sensing antenna get it. We compute the distance from this reflection. Then we have also here another metal plate. From the second target, we get the reflection, also we can sense it, and then also this wave is also received by this receiver antenna, and we use communication here. So we don't use any separated ranging slot or something like this, or any special sequences. We sense the reflected frames, data frames through data which goes to this user, and we use the reflections for the sensing. How it works, this is a very typical actually architecture. We have firstly 4 QAM modulation, then we do our OTFS processing. We use this inverse symplectic fast Fourier transform. So actually here we go to the frequency domain. We use filtering and rate conversion for USRP in frequency domain. Then we use IFFT, cycle prefix addition preamble, and we transmit it. Then in the receiver, what we do? First, we fix this OFDM overhead. So we remove cyclic prefix. We do rate conversion from USRP from 200 megasamples per second to 160 megahertz. Then we do in the frequency domain hardware imperfection equalization, because in USRP, those filters are affecting our signals with side lobes. So we remove it here. Here we use frequency domain, for example. Then we use division in frequency domain to get the channel impulse response. So this is also frequency, and then windowing, background cancellation, and so on. And here is a symplectic fast Fourier transform. So we go to the delayed Doppler domain, but this is actually equivalent to fast and slow FFTs in OFDM. So this part of the sensing processing for OTFS is identical as for OFDM, and we can prove that according to the amplitude of these delay Doppler heat maps, SSFFT is identical as fast and slow FFTs in OFDM. So those are the same actually processing concept for OFDM on OTFS, and the sensing is similar. So this is the result. So we have the wrong hole, what we have in IHP, the sensing element, 2 targets, and we see very nicely these 2 reflections, 195 centimeters, 6 meters 1, and we can see the range very precisely with those peaks, and this ranging works pretty well. Accuracy with 1 target, it is ±4 centimeters, and this is due to the reason that we have actually an periodogram method which interpolates the incoming signal in frequency domain. Therefore, this error with 1 target is very small. But of course, this depends on the SNR. If we have high SNR, this method can work. If you have limited SNR, then it will be not working, and the result will be much worse. Thank you, everyone. That's all from my side. I am ready for your questions.
Thank you, Lukasz. Maybe just one quick question before we go to the audience question. So is OTFS the only waveform that is studied in the project, or there's also other waveforms under consideration?
No, there are quite many different waveforms, and actually OTFS is only a small part of it. The details I don't know because I'm very deeply only in this OTFS team, but there are also other waveforms.
Okay, good. So we have lots of questions about OTFS actually. So the first one is, for low latency application, can OTFS be adapted to allow fast decoding? Because to decode the symbols, you need to receive the entire transcript matrix.
Of course, this is very big problem. Okay, I don't know whether very big problem. We could do not consider too much latency, but one of these problems is that you, instead of receiving a single vector, now you have to receive a complete matrix to decode it. But this is only one problem. Another problem are bit detection algorithms for OTFS, which are quite heavy for computations. You have to, it's more complicated than for OFDM. The base concept of going from time domain to the delay Doppler domain is simple, like in OFDM. But equalization, let's say, yes, equalization and bit detection for OTFS is very heavy. And there you will also lost a lot of time. So OTFS, if you will see for low latency application, this how we do it and how I shown in these slides actually is not pretty low latency. It will cause a lot of computation effort, and latency will be significant.
The next question is a twofold question. The person first asks, why do we need OTFS and ISAC? And the second part is that OTFS is likely not to make it into the standard, 6G standard. So what is your view on that?
Yes, okay, first question, why we need OTFS for sensing? Actually, we don't need OTFS for sensing because, as I said before, in a few slides before, the sensing for OTFS is actually almost identical like in OFDM. So OFDM sensing can work exactly the same like for OTFS. So, so actually, if you will do it like I have shown here in those slides that you would use this division in the frequency domain, then my answer is OTFS doesn't bring you any benefits in the sensing because the same you can do in OFDM. Only if you would use directly this channel, pilot-based channel estimation in delay Doppler domain, then you can reduce some computation effort in OTFS because this sensing you will get completely for free. So this is only the case which is improving for OTFS and which is giving some advantages over OFDM, but we did not yet try it. We have on our to-do list to follow this strategy, but as I have shown in the slides, actually you will not have any benefits in sensing as compared to OFDM. Second question, whether it will become a standard. Okay, this is a very difficult question. I know there is a huge lobby for promoting OTFS to be a standard, and many papers they start immediately if they publish something, some transaction journals or anything. The first sentence is that OTFS is a very promising candidate to replace OFDM and it will be standard in 7G and so on. So we are very actually careful claiming something like this, and I wouldn't take a risk to say like that because in OTFS there is still a lot of to do. So before it will be such mature system like OFDM, we need still some time. And actually there are a million papers which research OTFS, but now we need to find this algorithm and this processing concept for OTFS, which will provide us such a reliability like OFDM. Because if we compare OFDM with OTFS, then you will see OFDM in static channels is really perfect. Everything works there really perfectly, and there is a huge gap between OTFS and OFDM. So OTFS for now, I think, cannot such easily replace OFDM, but maybe in only some dedicated scenarios when we have this very high Doppler spread, then it is maybe a free room for OTFS, but OFDM for static channels is very well suited.
Thank you. As you heard, the music announced
Yes.
the end of the slot. There's a bunch more questions in the chat. I hope you have some time to hang around and answer them through the chat function. We need to move on to the next presentation.